Hello and welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this video we'll look at decomposing signals in components. These are the topics that we'll go over. We won't be going into much detail, but just to give you some intuition about either how they work or what their applications are. So the very first one is principal component analysis, which you probably already know by now. We have covered this in the previous videos as well. Let's say we have these orange data points and we are trying to find the direction of maximum spread. One way to do that is draw, let's say, uh, because this is a 2D set, we can draw a line through this to find the maximum direction. And here we can see that the magenta line is perpendicular to the blue line that's coming from the orange dots. So what we want to do is minimize the length of these total length of these magenta lines. And to do that, we can see if we project, in this case, if we project these points based on this position of the line, then we get this projection of PCA, which is by light green color. And if we put the dotted line in this particular direction, then we can get this projection. And in this projection, it looks like the distance of these orange dots from the blue line are much closer. So maybe this could be the best projection. And so this would be the first principal component that explains most of the variation in the data. So based on that, then there is sklearn also offers uh, different types of PCA implementations. So in general, PCA, as per the docs, it uses batch processing. And in incremental PCA, if it's a large data set, then this can be used where the data is sequentially fetched and to perform the PCA. There is also called as PCA using randomized SVD. So let's say, for example, we have this original matrix right here. We can decompose that matrix into three different parts: U, S, and V transpose. Each of these parts have different names. So the middle one, which is the S, is the singular values, and the U would be the left singular vector, would have the left singular vectors, and the this one would have the right singular vectors. And the way randomized SVD works for PCA is that the singular vectors or components with low singular values, they are dropped. And that's how this method works. And if we can combine US and T again, as shown here, to get back to the matrix that looks like original, that is closer to the original matrix. So the takeaway message from this slide is that in this method, if the singular values are lower, then those corresponding singular vectors are dropped. Here is an example on the faces. So this was a data set where I had 10 different images with different facial expressions, and using randomized CV, we can see that these are the components, the 5 components that the method was able to find. And we can see the features such as eyes, nose, the mouth, etc. In these representations. Next is Kernel PCA. So this is used for nonlinear dimensionality reduction. Here we have a data set shown in the yellows dots and the blue dots. If we perform PCA projection, we get this plot that's shown above. If we perform a kernel PCA projection, for example, using RBF in this case, which is the radial basis function, then we get this plot. And we can go back from the projection to the original data as shown here. It's not exactly what it was in the original data, but it's closer to, it's much closer. So that's the kernel PCA. Then we have sparse and mini-batch sparse PCA. So in case of mini-batch mini-batch PCA, mini-batch sparse PCA, as the name indicates, uh, the processing is based on mini batches of data as compared to the sparse PCA. And what the sparse PCA does is, uh, here is the representation again of the same images, 10 images. I've shown here only 5 components where uh, sparsity is induced, so we can still see the features such as eyes, nose, and some facial expressions as well. And here is the objective function for that can be minimized while using this method. Next we have dictionary learning and mini-batch dictionary learning. So in mini-batch dictionary learning, you are working in batches as compared to dictionary learning. And what I mean by dictionary here is a matrix where each of the columns is called atoms. And this is then the objective function that is minimized in case of dictionary learning. And on the right hand side, we see the representations of the images from this particular method of mini-batch dictionary learning. Then let's look at what is factor analysis. So very briefly, let's say we have these observed factors, which is sweetness, creamy. Let's say think about this as we are talking about ice cream. Then we have how sweet it is, how creamy it is, are there any toppings, and what is the color of the ice cream. So based on this, if we are trying to find out what unobserved factors could be related to these, then that's where the factor analysis comes in. So let's say we have two factors, F1 and F2, that we are trying to find. Then those can be found based on the weights that these would have on each of these observed factors. And these unobserved factors in this case could be processing. So processing could have an effect on how sweet the ice cream is or how creamy it is. And a region, maybe region could have an effect on what color is put in the ice cream based on the choices of the people or what toppings are put on the ice cream. So that in general is represented by this linear form where y is equal to w, which is the weights, into f, which is the unobserved factors, and plus a error term. And here is a more formal representation from the docs. We have the data x, and this can be represented in a linear form as shown here, where w is the factor loading matrix, so weight matrix, and we have the error term and we have the m term here. So error again is denoted by this distribution. And this linear combination can also be written in terms of probability, which is shown right here. Probability of x given hi, and this again is given would come from a normal distribution that is listed here. And on the right hand side, we can see the representations from factor analysis, and with with again with this particular images, we can see that it is able to capture the facial expressions and also the features, eyes, eyebrows, etc. And along the same lines, there is another technique called independent component analysis, and here we can see the representations from those. This is for image processing. In addition to this, there is another application in audio processing. So let's say we have a audio of uh, three sources, mixed audio coming from, and that mixed audio has three different audio sources in it. For example, this blue graph here. So independent component analysis can be used to separate out each of the three signals as shown here. And we'll be working on a project in upcoming video on exactly this problem. Next is non-negative matrix factorization. So in this case, uh, the method assumes that the data and the components are non-negative, so they're all positive. And here is the idea is to find the distance between the data x and the product of w and h. And that distance can be found by this Frobenius norm, which is given by this equation. And down below here is the objective function that is minimized in the scikit-learn implementation, where these alpha and the rho terms are used uh, for controlling the regularization. There are other distance metrics that can be used in scikit-learn, which are listed here. We have the squared Frobenius norm that we saw earlier. Then we have KL divergence, and we have IS divergence. And down here, this equation just shows the general form for these distances. And here is a collage of all the representations from all the different methods that we have seen. We have PCA using randomized SVD, NNMF, fast ICA, factor analysis, MiniBatchDictionaryLearning, and Sparse PCA. Finally, let's look at latent Dirichlet allocation, LDA. So in broadly speaking, the idea is that let's say we have a couple of documents and we need to find the topics to which each of these documents would belong to. We do not know the topics ahead of time, so but we do know what words are there in each of these documents. So let's say this first document has run, football, apple, and so on for the other documents. So what LDA does is it helps us find what the topics to which each of these documents belong. So maybe fruits is one topic that it is able to find, and sports is another topic it is able to find. Now, if you look in the docs, this is the diagram that is given. I'll try to explain this. I hope I don't confuse you. So the general idea is that you start with alpha and this parameter nu. So this is the per document topic distribution. What I mean by that is, let's say we have this Dirichlet distribution, which is shown here by a triangle. What this suggests, and if you can see, there is the intensity of the color is darker at the corners and a little lighter in the middle. So the idea is that probability values are higher at the corners than at the center. And let's say each of the corner represents a particular topic. So this could be maybe this food, travel, and cities. So those could be the topics. And then within each, in here, there are dots. So each dot represents a document. So the closer the document, the dot is towards a corner, it means that higher is the probability for that particular document to be associated with that topic. And so each dot then can be represented by this distribution that is shown here. We have the green, uh, maybe it corresponds to this topic, and then some of the other two topics that is shown here. On the right hand side, let's say we have more than 3 words, so we are putting a more than 3 words, so we're putting a 3D figure here. So we have each of these corners representing a special word, and then the green dots represent a topic. So that similar to this case, we can find out the distribution of the topic per topic word distribution as shown here. So closer the dot is towards this particular corner means that those words are related to that topic. And this is the iterative process. So what you do is you you're drawing the topics and words from these distributions, and then you're create so with the theta d, what we are trying to do is finding the topic distribution for the document D, and then with Z we are drawing a topic from that distribution and creating a list of that. And from the beta we are drawing the words, and then here we have in WD, which is where we draw the observed word from what we get here. And so in the end we form a document, and the document is then compared, and so we compare the distance of the document that was generated by LDA with the original document to find out which to maximize the probability to find out to which topic that particular document would belong to. I hope I gave you some intuition, and at least I hope I didn't confuse you. If you have any comments or questions, please let me know in the comments below. I hope to see you all in the next video where we'll do some hands-on coding on some of these topics in decomposition. Until then, please like, share, and subscribe. Thank you.